Morning all. Today we will discuss the power consumption. So it is one of the dynamic characteristic of CMOS device. In the last class, we have discussed the propagation delay and the transition time of the CMOS device. So today we will discuss the power consumption of the CMOS device. So as far as concerned with the integrated circuit, the amount of power or the power dissipated in an integrated circuit is in the form of the heat, and if the excess heat is generated, so it causes to damage the integrated circuit. So therefore always the power consumption or the power dissipation so must be low. So it is one of the desirable characteristic. So which is always must be low. So one of the trade-off of the VLSA design here. So if you see the trade of the VLSA designs, the first one is the area, and the second one is the power consumption. In the point of VLSA design, if we see the area, power consumption, these are all very desirable characteristics. So here the power consumption is one of the trade-off for the VLSA design. So our digital circuits are the integrated circuits. So the power dissipated in an IC is in the form of the heat. So the excess heat can damage the digital ICs. So therefore the power consumption is always to be a low value here. It is advantageous that the power must be as low as possible. So here the power dissipation of a CMOS IC is very low when it is in DC condition. So what is a DC condition here? The DC condition, it refers to the static condition or the steady state condition of the CMOS device, because we can describe the behavior of the CMOS device at two different points. One is at static condition and the second is dynamic condition. And in the yesterday and day before yesterday also, so you were asked a question that what is the difference between the static and the dynamic electrical behavior. Static and dynamic, the same thing is now the DC and AC condition. Static is the DC condition, dynamic is the AC condition. So in static condition, input and output are fixed to a state. So they will be fixed to a particular state, low state or high state. So when the input is a fixed state and to that a corresponding the output state, and the output is also at a fixed state, under that condition the power dissipation or the power consumption of the CMOS device is referred with the DC condition. So simply it is when the output is at a fixed state. The power dissipation of the CMOS IC when the output of the CMOS device is at a fixed state. So such condition is referred with the DC condition. Then what is AC condition? Dynamic condition. In dynamic condition, the output of the CMOS device is switching between the states here. So the output state of the CMOS device changes between the states here. So when the output is switching between the states, it will consume or it will consume a significant amount of the power here, because under such conditions, so there is a transient current for charging the capacitance and for discharging the capacitance. So here the power consumption or the power dissipation will be evaluated under the two conditions here. One is DC condition and second one is dynamic condition. You can also say AC condition. So when the CMOS IC is in DC condition, the power dissipation of that IC is very low. So almost we can ignore it. There will be a power dissipation, but comparatively the dynamic power dissipation, it will be a negligible one, or it is a quite low value. But the power dissipation of the CMOS IC increases in proportional to the frequency at which the circuits are switching states here. So when the output is changing between the states, when the output is changing between the states, so at that conditions, the CMOS IC power dissipation or the power consumption will be increases rapidly here, because it depending on the frequency at which the circuit is switching between the states. The frequency at which the circuit switching between the states. And here when the CMOS output switches from low to high or vice versa, high to low. So when the CMOS output switches from low to high, a transient charging current has to be supplied to the load capacitance. And when the CMOS output switches from the high to low, second condition is high to low. So again, there is a transient current, which is the discharging current from the load here. In the first case, low to high, in the first case, low to high, where the stray capacitance will be charged to its maximum value. So therefore, it is the transient current which is to be supplied from the VDD to the load capacitance. But the second case, if you take, that is high to low, that is high to low. So in this condition, the stray capacitance will be discharging here. From which value? From the high state to the low state. So when the CMOS output switches between the low to high state and high to low state, a significant amount of current has to be supplied to the load capacitance, or a significant amount of current will be drawn from the load capacitance here. So here, as the switching frequency increases, the average current drawn from the VDD also increases, resulting increase in the power dissipation. So that's why the AC condition power consumption or the dynamic power consumption has a significant in the power consumption. Rather than the static condition or rather than the DC condition, the dynamic or the AC condition has a more significance here. Why? Because when the output is switching between the states, so it draws the more current from the VDD. So because of that, it increases the power dissipation here. So this is the source, one of the source, how the power will be conserved or how the power will be dissipated in the digital ICs. Next one. So rightly we said the power dissipation of the CMOS circuit at DC condition is called the static power dissipation. So what do you mean this static power dissipation? When the output is at a fixed state. When the output is at a fixed state, and if you determine the power dissipation at that condition or at that point, so the power is known as the static power dissipation. And the second one is the power consumption during the transient. So here the transient may be a low to high state or high to low state. It is a low to high state or high to low state here. So that is the transient current for charging and the transient current for the discharging. So now under this dynamic condition, the power dissipation is called the dynamic power consumption. It is called the dynamic power consumption here. So now the power consumption during the transient is given by, because say if you want to determine the static power first, if you want to determine the static power, say it is very easy that you can let's say the power dissipation at the DC condition. So DC condition, static condition. So simply you can take the P equal to VI. P equal to VI. So that is from the CMOS VDD and IDD. The product of the voltage and current that gives us the simple DC condition or the static condition power dissipation. And again, if you see this IDD, here we will have the two types of the IDD currents here. One is IDDH and the second one is IDDL. So what are these IDDH and IDDL? IDDH. It is the drain current of the transistor when the output is at logic high state. When the output is at logic high state, what is the amount of current that is drawing or for the output? And then what is IDDL? IDDL. So it is the drain current at the output of the transistor when the output is at low state here. So now the IDD current is the average of these two currents here. So therefore here the term that can be VDD into IDD average. So the static power dissipation can be easily determined P equal to VI, where V is VDD and I is IDD, supply voltage and the output current. But this output current again of the two components here. The first is the amount of current that can be drawn at the high state of the output and the amount of current that can be drawn at the output when the output is at low state. So now you have two current components. So now the actual IDD is the average of these two here. That is IDDH plus IDDL by 2. IDDH plus, I'm just simply writing it as IDDH plus IDDL by 2. So now this gives us the IDD average. So now the product of these two will determine the static power here. So it is the easiest thing. You can easily determine the static power dissipation. The static power dissipation. Now see. Now what about the dynamic power dissipation here? The power consumption during the transient is changing the state, is given by the PT equal to the power consumption during the transient, PT is equal to CPD, which is the power dissipation capacitance, and the VDD power supply and the transient frequency here. So here where the PT is the circuit's internal power dissipation during the transitions. So when the output is changing between the states, so here we are determining the dynamic power consumption during the transient, that is PT, internal circuit's power dissipation, and where the VDD is the power supply here. So where the VDD is the power supply voltage, and the power dissipation across the resistive load. The power dissipation across the resistive load is proportional to the square of the voltage. So that's why here we have the square, VDD square, the power supply voltage. So it is the power dissipation across the load, resistive load, is the proportional to the square of the supply voltage. So that's why here VDD square. And this next one is the transient frequency of the output signal. So transition frequency of the output signal. So this specifies the number of power consuming output transitions. So this F specifies that the number of consuming power, I mean the output transitions per second here. So that is the number of transitions per second. So that will be divided by 2 in practical cases here. Transitions, low to high and high to low. So the F is the transition frequency of the output signal. And then the next parameter is the CPD here. So here the power dissipation capacitance, and which is usually specified by the manufacturer. So here example also you can see for a HC series CMOS gates, the CPD, the power dissipation capacitance value is typical of 20 to 24 picofarads here. So using this formula, we can determine the power consumption during the transient. During the transient here. Next one. And here if you see the above formula, so this one. So the above formula is valid only if the inputs are fast enough. So when the inputs are fast enough, as a result, the outputs also switching fastly here. Okay, so whatever we seen here, the power consumption during the transition, so this is valid only when the output is having the fast switching. When the output is having the fast switching, as a result, the output is also switches its states fastly. But if you see the second condition, because one is the inputs are at fast enough, and the second one is the input transitions are the too slow here, because the output of the circuit will change according to the condition of the input, 0 or 1, according to the logic value at the input. So there will be an output here. So if the inputs are fast, the output also fastly changes, or it is fastly switching between the states. Suppose if the input transistors, if the input transitions are too slow, then the output transistors stay partially on for long time and the power consumption increases here. To understand this, so if you take the static condition, where in static condition we assume that, or we think that the change of state is occurred immediately, say, because all the time we will see only one state at the output, either 0 state or 1 state. But in the case of the transition, take this is a transition input. But in the case of the transition, you will have the 0 to 1 and 1 to 0 transition. 1 to 0 transition. If the inputs are fastly switching, according to that there will be a changing in the output. But if the inputs are changing slowly, so what will happen? So depending on the logical values at the input, the CMOS, the transistors in the CMOS inverter circuit, so they will be on for more time here. So when the transistor is on for long time, so it obviously consumes more power here. So here the second source of the consumption is the capacitive load. So here two conditions are taken into the consideration. One condition is when the input is switching between the states, there will be a switching between the output states also. So because of that switching states, there will be a power consumption. That is one point. And the second source of the power consumption, it is also a significant power consumption, is a capacitive load on the output here. Even in our last class also we have discussed the rise time and fall time of the transition time. It depends on the two factors. One is the on transistor resistance and second is the stray capacitance at the output. So here the second source of the consumption is the capacitive load on the output. And in each case, how we can say here the capacitive load, during the transition state, low to high, during the transition state, low to high, during the transition state, low to high, the stray capacitance is charging for the maximum stray capacitance value, charging for the maximum stray capacitance value. So the current is flowing from the VDD to the P channel resistance through the capacitive load. And during the high to low transition, if you see the high to low transition, so now here the stray capacitance will be discharging here, the stray capacitance discharging. So here the stray capacitance is discharging through from the capacitive load through the N channel transistor resistance through the ground. So in each case the power is dissipated in the on resistance of the transistor. So how we can understand this point here? So here we are saying that capacitive load is the another source of the power consumption. So in capacitive load, if you see during the transitions, the capacitive load is realized by the dynamic condition. It is realized by, or it is modeled by the dynamic conditions, AC condition, AC load. So during the AC load, the output is switching between the states, that is low to high and high to low. So in either of the transitions, if you see one transistor is in on and other transistor is in off, so therefore in each case the power is dissipated because of the on resistance of the transistor. In low to high, the P channel resistance. In high to low, N channel resistance. N channel resistance here. So now again here, if there are two F transistors per second, okay, so now, so under this capacitive load, we want to determine the power consumption again. So for determining the power consumption, it is said to be the power consumption. So it is said to be the power consumption due to the capacitive load here. So now we will determine the power consumption due to the capacitive load. In previously, the power consumption due to the transient. Now the power consumption is due to the capacitive load. So for to determining that, say if there are 2 F transistors per second. So if there are 2 transistors per second, see if you see in the dynamic condition, so the 2 transistors are partially on here because of the low to high transition and high to transition at the fast switching. So if there are 2 F transistors per second, the power dissipated due to the capacitive load is given by the power dissipation due to the capacitive load is given by the same formula, CL into VCC square. I mean that VDD. If it is a BJT transistor, you will get the VCC square. If it is a mass transistor, you will get the VDD here, VDD square. VDD square by 2 into 2F. So because the number of transistors per second are the 2F, 2 transistors, P channel and N channel. And here it is the average of the charging voltage. It is the average on the charging voltage. One is for transient charging and second one is transient discharging. So therefore here the transient charging voltage and discharging, the transient discharging voltage, the average of 2, this will gives us the voltage of the capacitive load. So that's why here the VDD square square by 2. So that's why here we have taken the VDD square by 2. So here the square is, it is because of the power dissipation across the resistive load is proportional to the square of the voltage. So because of that it is the square, and by 2 is, it is the average voltage, because we are seeing this is as a capacitor. So for the capacitor charging and discharging, okay, so for that, so here it is the average, so the VD square by 2 here. So here it is the power dissipation or the power consumption due to the capacitive load. Now, what is the total power consumption of the CMOS IC here? The total dynamic power, of a CMOS circuit is the sum of the PT and PL. So here the PT is the power due to the transient, low to high and high to low. Again, in all the time we are discussing the only the 2 points, low to high and high to low only, because it is a dynamic condition, and the power due to the capacitive load. So now the total dynamic power is the PT plus PL. So that is the CPD into VC square into F plus, and again the capacitive load CL VC square into F. So here the 2 and 2, these two will get cancelled here. Again you will have the same equation like of the PT, power due to the transient. So finally here the total dynamic power is CPD, the power dissipation capacitor and the capacitive load into VCC square, that is VDD square into F here. So this is the power consumption of CMOS digital IC. So for conclusion for this power consumption, so here the power consumption is, it is because of the two. One is the power consumption due to the switching between the states, and the second one is the power consumption due to the capacitive load. So that's why here we have PT plus PL. So did you understand this power consumption of CMOS? So did you understand? So with this, we completed the CMOS electrical behavior. We completed the CMOS electrical behavior. So this is very, very important, the CMOS logic circuits. So till now, right from the beginning, we have started with the introduction to the digital ICs, and we have seen the classification, logic levels, and we have seen the voltage logic levels of the CMOS logic, and after that we have seen the CMOS logic circuits. So we have seen the CMOS logic circuits in 3 different categories. One is CMOS inverting gates, CMOS non-inverting gates, and the third one is CMOS AOI, OAI gates. And after that, the behavior of the CMOS device. The electrical behavior can be described in 2 ways: static behavior, dynamic behavior. The static behavior, it is also called as the steady state or the DC condition. So, and in steady state, so there are different characteristics are there. So they are known as the DC characteristics or the steady state characteristics: logic levels, noise margin levels, CMOS behavior with the resistive load, CMOS behavior with the non-ideal inputs, CMOS behavior with the unused inputs, fan in, fan out, loading effect. So these are all the static or the steady state or DC characteristics of the CMOS device. And the dynamic characteristics are only 2. One is the speed of the CMOS device and second is the power consumption. But the speed is depends on the two characteristics, transient time and propagation delay. Okay, and here the transient time, it depends on the two times, rise time and fall time, TR and TF, whereas the propagation delay, it is determined by the two timing intervals, that is the TPHL and the TPLH, the propagation delay to change the state from the high to low state and vice versa, low to high state. And the second dynamic characteristic of the CMOS device is the power consumption. So here the power consumption, it is because of the two. One is the power consumption due to the transient, which is the change of states, and the power dissipation due to the capacitive load at the output. So this is the electrical behavior of the CMOS device. So did you understand the overall behavior of the CMOS electrical behavior? ఏం అర్థమైందా మీకు ఇప్పటి వరకు అయిన దాంట్లో ఏమైనా డౌట్స్ ఉంటే మీరు అడగండి. ఇంకొక 5 minutes ఉంది మనకి టైము. And coming to the assignment, so you need to submit an assignment on the CMOS electrical behavior. So in that assignment, so you need to answer for the first one, explain the steady state behavior of the CMOS, and the second question is explain the dynamic behavior of the CMOS. So you need to write write for the characteristics of the steady state behavior and the characteristics of the dynamic behavior.